Well, so for you especially that you don't know me, I'm Luis Garcia-Mozos, and I'm going to present my research project that is BFS, Back from Space, and it's supervised by Stefan Heinrich from e.NOVA Aerospace. So the main goal of the project is to develop a reentry kit that is capable to retrieve payloads from the space back to the ground in a safe and controlled way. And for that, we summarize it in this 12 focus work of the project that entail all the tasks that have to be completed, from the trajectory and system definition to aerothermal, mechanical aspects, and materials, and also the customers and products and funding of the project. So we did in April a little review of the state of the art. I showed you these two examples of the deployable accelerator by ADAPT and the inflatable one by Festo, and that both of them have very interesting points for our project and points in common for the project as well. We presented this timeline back in April, and now we're going to focus mainly on these two points, the trajectory and landing definition, the system definition in particular with the propulsion module selection. That is what I have mainly done this month. So let's start with the trajectory and landing. First, well, this is a very complex problem, the study of the atmospheric reentry, so we are going to go step by step. We start with a survey of the possible locations for the landing, and we will then analyze ideal descent, supposing no atmosphere, supposing a Kepler trajectory, and that will be the starting point to use a software from KNS called the RISC to simulate the atmospheric reentry, and then tune the parameters to have a nominal case, and from there introduce perturbations to see how they affect to the landing position. So for that, we will start from this basis scenario of descending, retrieving a 4 kilogram spacecraft for 400 kilometers, so in the surroundings of the ISS orbit, to the ground. And this is the first choice that we're making here, is that we want to land on ground and not on the ocean, because even though it will be more challenging to have this accuracy, the recovery will be easier, and you don't need a fleet of ships and so for the recovery on the ocean. So first we did this survey on the possible landing locations on ground. We show you some examples here of places that we studied. You did some training range in the US, somewhere in the Sahara Desert, and also some places here in France or even in Spain that are too small for our purpose, because we only have around 40 kilometers of range. And we definitely found this one, Woomera Range Complex in Australia. That seems to be the best possible landing location. Is a very big protected area of in the diagonal up to 600 kilometers of dimensions. But there's a but, and it's of course that we cannot optimize these dimensions, because the landing trajectory will be submitted to the inclination of the orbit. In this case, we are in the ISS orbit, so 51.2 degrees. I show you in the picture the footprints. So we cannot optimize perfectly these directions, but we still found some ranges in the surroundings of 300 kilometers. And we would even have to do a more accurate study of this, because I'm sure that we can even reach more than that. And it's, of course, more than anywhere else that we have found for the moment. So now that we have a possible landing area, we will use it for this nominal case, and let's see if it's possible or not to land in this area in the simplest possible design, because we are focusing on the design of a 3U spacecraft that has to include everything. So we cannot put an active guidance system. So we have to see if it's possible just with defining the trajectory after the orbit band. Is it possible to land on this area? From literature review, we found, for example, that driver will be the time in reentry. So the less time, the better will be not to deviate from the pure ballistic and ideal trajectory. But this, of course, also affects the heating rates and so it has to be managed. And main sources of error will be in the orbit impulse, the initial position and attitude determination, the aerodynamic model, and in particular the ballistic coefficient determination that we'll talk about now. So to analyze this, we start by the ideal case of a Kepler motion from the ISS orbital plane. So we have the inclination and the run defined with that. And the shape it will be this one that I show you, an elliptical transfer with the apogee at 400 kilometers, the perigee on the Earth. We do the average, we have the semi-major axis, and with the other, this ratio, we have the eccentricity of the orbit. Now, for the argument of the perigee, is the first time that we put into place the landing coordinates, and in particular, this will depend on the latitude of the landing place. So we do some spherical trigonometry, and we get this expression, and from here we can get this value of 320 degrees for the argument of perigee to reach Woomera latitude at the perigee, so at the minimum height altitude. Then we have to impose also the longitude of Woomera, and in this case is with a timing. So it's the first time that we introduce the time here, and we have to find the temporal window for launch to land in Woomera. So for this, we first define where the ascending node will have to be in order to, after a complete orbit or almost a complete orbit, reach the longitude of Woomera. We take into account here some spherical trigonometry again, the effect of the rotation of the Earth, and here we have 179 degrees of longitude for the ascending node. With this, it's a direct differentiation to get the Greenwich sidereal time at the ascending node as well. And it's a value of 176 degrees. This happens around once a day. And for these examples, we will take a nominal date on the 1st of January of 2022. And this will happen at 5:03 in the morning. So this will be our first reference. Then we compute the time that goes from the ascending node to the apogee. That will be our starting point. And just with some basic calculations of orbital mechanics, we get this expression for the increment of time, introduce the eccentric anomaly of the apogee and of the ascending node, and we get the 43 minutes and 35 seconds ongoing from the ascending node to the apogee. So now at this T0, we were in the ascending node, we sum this quantity, and then we are in the starting point from the apogee that will be at 400 kilometers. In this chosen day, it will be the 1st of January 2022 at 5:46 minutes 45 seconds in particular. So now we have defined a nominal case in Keplerian considerations, just taking the orbit parameters into account and the time. So we will be completely close the problem. Now, we are going to use the software libraries from KNS to take into account the effect of the atmospheric reentry and of the drag coefficients and so. So we are going to take the reference of a 3D device with complex geometry that we are not going to simulate here. We are just taking a equivalent sphere of, just for this matter, mass of 4 kilograms at 50 centimeters of diameter. We suppose no ablation, so for that we impose an ideal material with perfect thermal properties. And the step we come in here, we cannot start the simulation from the apogee, but we start the simulation from nu equal to minus 90 degrees. So we just completed the previous step to get this time at 625. So we introduce these parameters of the Keplerian orbit, we simulated, represented in Google Earth, and this is the result. The yellow landing area that you can see on Google Earth is Woomera. And we see that, of course, it doesn't reach the landing area because we were supposing an ideal motion. We weren't taking into account the drag. And of course, it falls before than expected. So we have to adjust the parameters, and we have some degrees of freedom. For example, we can increase the altitude of the perigee to force it to fall later. We can increase the altitude. We can increase the argument of the perigee to take it to the north, and it will be the same effect. And finally, we just have to adjust a little bit the time to fulfill these constraints as well. In this case, we chose to leave the perigee at 0 kilometers, and we just moved the argument of perigee. And I move it to remember that before it was 320 degrees, and now we moved to 13 degrees. So we moved to the North Hemisphere in order to land in Australia. And okay, and now with these new parameters, I saw you the picture from Google Earth that we reached the landing, and we see the green push pin, and we reached the landing on Woomera. So now we have a nominal case that works with those parameters. Now let's tune the variables to see whether their effect. And I can advance that the mass and the diameter will go together in terms of ballistic coefficient. And in particular, I just want to highlight that I will use the reduced ballistic coefficient, so just mass over area without taking into account the drag coefficient in this case. I will also study the perigee altitude and the argument of the perigee. So first, introducing variations on the ballistic coefficient. I simulated here 99 different spheres with masses from 3 to 5 kilograms in increments of 0.5, and for each of them, I introduced diameters from 40 centimeters to 60 centimeters in increments of 5. And remember that the nominal case was 4 kilograms and 50 centimeters. And this is the result. All of them fall within the predefined area. The ones that are more to the north, let's say, are with higher ballistic coefficients than the nominal, and more to the south, or falling earlier, are with lower ballistic coefficients. Now we process this data a little bit with Python and MATLAB. And in this case, we represented the variations of the downrange, so the distance on ground, against the ballistic coefficient. And we see first what we expected, the distance increases with the ballistic coefficient. And what is more interesting is that there's a second order progression, and the curve is concave, tends to be flat for high values of the ballistic coefficient. So this is also what we expected from literature review, that higher ballistic coefficients give better landing accuracy because it reduces the time and reentry and so. But of course, again, we will have to have other drawbacks in compensation. So we use a second order regression. We derivated, we introduced small variations, and I got this expression for the small perturbations of the downrange of the distance on ground as a function of the small perturbations in ballistic coefficient. We do the same for the final velocity. That will be other interesting parameter because it will determine the landing system, and we see a similar trend. And I also interpolated and got a second order regression. Again, the final velocity increases with the ballistic coefficient. So this is one of the drawbacks that I mentioned, because we want to be landing as low velocity as possible, and if we increase the ballistic coefficient, it will be bad for that purpose. Now we introduce variations of the altitude of the perigee, similar from minus 5 kilometers to plus 5 kilometers in increments of 0.5. This is the representation in Google Earth. We do the same as before, representing the distance to the nominal position of landing as a function of the altitude of the perigee. And now we see that we have a linear tendance, a linear regression. We derivated again, introduced small variations, and we have that for 1 kilometer of increment in the altitude of the perigee, we have around 31 kilometers of distance in the landing position. We do the same for the torsion velocity, and in this case is constant, so we suppose that they are independent variables, at least with this approach. Now, argument of the perigee, again, we introduce from 12.2 to 14.2 degrees, increments of 0.1. We see that the whole orbit is displaced to the northeast in this case. And this is the representation again. All of them fall in the area. We do the representation in MATLAB. Again, it shows a linear tendency. In this case, even a perfect linear regression is what we get. And we see that this is a very sensitive variable because for 1 degree of change in the, this is in degrees, 1 degree of change in the argument of the perigee, we have 110 kilometers of difference in the downrange. And again, with the velocity, it's almost independent. Now, we want to combine all these parameters and give an example of a worst-case scenario of all of them going to the same tendency. I show you here the example for going to the northeast, as we increase in the ballistic coefficient, the altitude of the perigee, and the argument of the perigee at the same time. We have 2 proposed scenarios, one for each combination of signs in the opposite way. and of a 5% in the mass, 8% in the diameter, 1.5 kilometers in the altitude of the perigee, and 0.5 degrees in the argument of perigee. We simulated, and this is what we get. That is landing right on the borders of the area. So we can say that this is a good first approach to have some estimation of what can be good or bad in terms of accuracy. But of course, this is not so representative yet because we're not introducing the final geometry and other factors that will come into play, but it's a good first approach. And it's more interesting to validate the analytical expressions that we got before. If we apply the superposition principles for the previous expression, we have a combined expression for the overall perturbation in the downrange as a function of the three parameters that we're studying. And same for the velocity that only depends on the ballistic coefficient. We compare the variables without tilde that are given by the risk and the variables with tilde that are given by these analytical expressions, and we see that they're pretty similar. So it's a good validation, it's a good first approach to see that this expression can work. So in parallel to this, and let's move on to this part now, we were defining the propulsion module that can be used for this spacecraft. We start from this basic scenario of a 3U spacecraft, initial mass of 4 kilograms, to retrieve from the ISS orbit. In this case, we take 408 kilometers of altitude, suppose an elliptical transfer and before, and one single bar in the apogee to reach ground. So this will be the orbit. Again, we start from a circular orbit, and at 408 kilometers, we go to this elliptical orbit of apogee 408, perigee at ground. Average is the semi-major axis, and with the conservation of energy, we get this expression for the orbital velocity. We have the velocity in the ISS orbit, the velocity of the apogee of the transfer orbit, make the difference, and this is the orbit burn necessary, 120 meters per second in this case. So these are the requirements. We need a propulsion module that reaches 120 meters per second in a 4 kilogram spacecraft. It will be desirable to do it in a single bar and reduce time to improve accuracy as well. So we are going to tend to chemical-like propellants. And this is a very important constraint. We can only have one U for the propulsion module because in total we have 3 U's. So we need low electrical and power consumption as well because we cannot fit a full electrical and power supply subsystem. And in this case, we want something as simple as possible. So we thought about cool gas system, warm gas with low power consumption. And we did an intensive market survey with around 60 suppliers studied from the database of CubeSat.com. And in the end, only 8 of them were found as possible candidates, all of them fulfilling these requirements of 120 meters per second and low power consumption, fitting in 1 U. And at the same time, we see that all of them have some power consumption. So with cold gas systems, it was impossible to reach these values. So all of them are called warm gas systems. And in particular, analyzing these options, we propose PM200 from Iberian Technologies as one of the best options, one of the best candidates, because it offers 230 meters per second with only 12 bots during operation mode and 0.1 in sleep mode. It uses non-toxic bipropellant. And this is important. It has a good status of development because it's something that we would like to use in not so much time. Also, other alternatives, for example, could be Baco and some of the others. But of course, all of this is to be confirmed with contacting the suppliers. So as a summary of what we have done during this semester, we define the trajectory. And what's more important, we define a methodology to define this trajectory from Keplerian motion to in some iterations in the BRISC, and it's implemented also in MATLAB. So it's easy to adapt and extrapolate to different scenarios. And with that, we get a nominal case that we can then use for the aligning accuracy study. We confirm that ballistic coefficient is a major driver, and we also analyze the effect of altitude of the perigee, argument of the perigee, and we provided some analytical expressions of how these variations affect to the final position accuracy. And we validated this with an example of worst case combined scenario. And in parallel to that, we selected a propulsion module. We defined that we need 120 meters per second for 4 kilogram spacecraft low power consumption and that can fit in 1U. And after an extensive market survey, we came out with 8 candidates, out of which some of them can be highlighted. And now, future work. We're moving to right now to a concurrent engineering design methodology with these 2 tools from KNS, CIC, and PASO. And this will be very useful. This will be a very good opportunity to include, for example, the real geometry in the landing accuracy study. And also something that has to be done in these terms is to translate this error budget from orbit parameters, that is what we have now, to operational parameters. So to delta V, time, etc. For example, the delta V can be related to the altitude of the nominal perigee, etc. And in terms of the propulsion subsystem, we have to confirm with the supplier the suitability of these systems and the cost to be taken into account. And finally, we will start sonarothermal analysis. Was one of the future works that we defined in the timeline. And in this sense, e.NOVA is in contact to get some sample tests of the flexible thermal protection systems at a plasma wind tunnel at DLR in Germany. And when that is more defined, I will probably work on that. And something that is of priority now is that we are in contact with the Orbit from Italy, that is a launcher and platform provider, for doing a prototype flight test. And for that, we need to develop a payload that is useful to recover all the possible data that we can. And in this sense, we would like to have a data recorder to measure parameters like the pressure, the temperature, the velocity, etc., and transmit it via Iridium link. And in that sense, I think I can help with this because probably we can reuse some knowledge and materials from the entries admission here at SupAero. So probably I will have to contact the people in charge of that project to see if they can help us with that. And that will be all. Thank you very much for your attention, and I'll be happy to answer any questions.